Okay, folks, let's go ahead and get started. Hopefully everyone had a good night last night, and let's give a round of applause to our sponsors from last night's social. That was pretty great, huh? All right, first up we have Petr Lapukhov from Microsoft.
Guys, good morning. Thanks for coming in so early. Last night was great, I agree. So I guess it's hard to come in this morning. I'll keep it short, and next 30 minutes we're going to talk about the project we had at Microsoft on data collection, on specifically Netflow, sFlow, and our template data collection for our network. It's called built-in scalable telemetry pipeline, but essentially it talks about mostly using big data for data analysis. So presentation is split into two sections. First one describes a problem statement, the problem we try to solve, and second one, bigger one, talks about the actual solution. So let's talk about the problem first. So the problem we deal with is the collecting a lot of data, mostly Netflow, JFlow, IPFix, all this kind of information from our devices, both from a core network and data center devices. As you know, there's a lot of use cases for Netflow data. It's very well known, capacity planning, building, all this stuff. The biggest difference and challenge for us was the scale we had to deal with. Well, if you start with core network, it's not that bad. I have maybe hundreds of devices, Netflow, IPFix. But once you move data center, once you start collecting data using sFlow, it gets much more challenging. So basic problem is that the volume of data is proportional to the traffic rate for sFlow. So you quickly hit the traffic rates of hundreds of megabits of data going to your collectors. And our specific of our system was that at Microsoft, we have, let's say, multiple groups that have slightly different approaches to data analysis. Let's say some people want to do real-time processing, and some teams want to actually archive and analyze data historically. And so for this to happen, people want to get the same feed of data in real time, basically, from multiple analysis systems. So this is specific. We want to get the data to multiple recipients at the same time. In addition to Netflow data, the other big thing we need to monitor is the Rosen State. In a presentation we gave before at NANOC, we described that our data centers use BGP exclusively for routing everywhere. And of course, BGP is a protocol in the core as an overlay routing system. So this way, collecting this data is crucial to monitor network health. And we need to capture the live state of all devices, all BGP tables on every device in data center and in the core. And obviously, for core boxes, this creates a lot of state, basically, full routing table. For data center, it's much smaller, but there's much more devices to monitor. And there's nothing special about monitoring. You just peer to all devices. The only challenge is with the amount of peering sessions you have to create to all these boxes in data centers. And the last thing is once you get all this data, Netflow and BGP, in your storage system, you need to analyze this. So the first challenge is the storage, because a Netflow and sFlow easily gets you to hundreds of terabytes and if not petabytes of data very quickly. Few months, and it's actually pretty full. And second one, the actual analysis, let's say just trying to build traffic matrix or trying to correlate BGP and Netflow data creates a huge amount of computation work, something which is not easy to do, say, using SQL database or using any other traditional approach. So we start with a solution now and talk about the collection infrastructure, or in other words, how we actually capture and store the data. So the first one, it's just a brief structure of the whole system. So let's say you have the guys who export the data, the routers. Then you get this data to a system which does replication and copies this stream to multiple recipients. And then these recipients do whatever you want. Let's say here there's a branch which says collect, store, and process, which is more like offline processing. And the other branch says just process, which is more of a real-time processing for Netflow data. As you can see, we only try to build one branch of this system. Let's say we call this offline processing. So we didn't want to actually process data in real time, let's say in order of seconds, respond in order of seconds. So we didn't want to have a solution for everyone, just build a system to collect this data and run some analysis reports on this. So exporting data is relatively straightforward. You get in every box, you enable Netflow, IPFix, sFlow, and send this data to a special IP address, which we'll talk about next. The biggest trick here is that number of devices is on the order of thousands. Let's say if you enable sFlow on every type of rack, so one data center is a few thousand of TORs, and the other one, same few thousand of TORs. This gives you like pretty large volume of data quickly. For sFlow, of course, we collect not just the flow data, but also the counters, interface counters, which is another nice part of sFlow. You can push the counters from every interface on the device to a collector system, which is more like SNMP, IFMIP being pushed to your collector. And of course, this data is always sampled, not because of the collector system limitation, but mostly because of the box that exports this data can't really handle traffic in a, say, 1-to-1 ratio. So the core boxes have to sample, the switch have to sample, everyone have to sample. And the problem is, of course, different boxes have different sampling ratios. And so now when you have this large volume of data in flight, you need to send it somewhere which can load balance, stripe, and somehow deliver this data to collectors. And we use this system we call SLB. It's called scalable load balancing. It could be server load balancing, whichever you prefer. But the system is a very simple load balancing solution, which is built in data center and uses two-stage load balancing. The first stage actually uses Anycast and BGP to spread traffic across load balancers. And the second stage is actually sends traffic to destination addresses. So as you can see, it's a very simple DSR solution, direct server return. But since it's so simple, it's actually very scalable. You can easily add more elements and grow the capacity of this pipeline almost to unlimited numbers. So the diagram kind of gives you an illustration of this concept. There's a very simple topology, the data center network. There are SLB elements, actual load balancers that get the traffic, and they even spread the traffic to the actual destinations or servers. So I mentioned the replication of data, and replication is simply done in load balancers. So as opposed to trying to balance traffic across multiple destinations, what you do, you take the packets and send them to all destinations at once. So the only limitation here is that essentially this implements some sort of edge multicast. So your load balancers have to copy packets and times proportional number of collectors and send them to destinations. So the only bottleneck might be the actual outgoing traffic rate at the box that does replication. But like I said, it's really easy to add more boxes to the system and increase the capacity. And also important to notice that there are multiple SLB systems in different data centers. And you export data to any cast IP address such that it always hits the closest one. And so this way you implement some sort of very simple global load balancing system. So you always pick up the closest load balancer and then just replicates data to the actual collectors. Collectors are just normal servers. When I say normal, it's not like very normal because we take them from these server pools, the fungible clusters that we have for our online services. So basically, there's a system which manages server pools in every data center, and you can easily provision new servers, deploy them, image them, and deploy your software very quickly. So you can basically add new collectors on demand from a common fungible infrastructure. This might be VMs, this might be actual physical servers, but it's really easy to add more collectors if you need. So once again, it's probably the last step of the collection. It's the scalable, horizontally scalable system to add in more collectors to a pipeline. And the nice thing is that SLB system, the load balancer, essentially partitions the data when it sends it to the servers. So basically, every server will receive just a portion or a partial view of, say, Netflow data or sFlow data. And none of these devices actually communicate to each other. We just store the data and then upload it to actual analysis engine. So it's really easy to scale this system by adding more components. And so this is one piece that doesn't fit in the previous picture. It's a BGP monitoring. So it's easy to collect and replicate UDP data, sFlow and Netflow. For BGP, it's slightly different. You have to pair all the boxes to monitors, right? And in this case, you have to send all peering sessions to one virtual IP address, which is also behind SLB. And the load balancer then will pick up some random machines behind the VIP to peer with. So what you get these thousands of devices peering, let's say, 5, 6 boxes, for example. And these boxes simply collect BGP updates and then also upload them to the storage analysis system. And well, once again, it's really easy to add more boxes if you need to. Let's say if you get more devices in data centers. But normally, BGP amount of BGP data is not as huge. It's not as hard to collect using just a few boxes. So let's say, okay, we get this data in flight on the collectors. Now we need to actually upload it somewhere and do the actual analysis. That's the most, say, challenging part. And so Microsoft, for a while, had the system on this Cosmos. And the Cosmos is somewhat equivalent to Hadoop, but it's, I say, Microsoft proprietary, Microsoft branded. It's built on a slightly different premises. It uses more, let's say, generic framework, not just MapReduce. It uses more complex infrastructure, more tricky abstractions to implement it. And arguably, MSR says it might be more advanced than Hadoop, but it's still like more arguments than actual facts. And so the key things about Cosmos, just like Hadoop, it provides you scalable storage, very simple storage for text files, and mostly for just log files, append-only streams. It scales to petabytes of data easily because it's just servers and the hard drives in one pool. And the only structure you probably have in the data streams there is that you partition them by time. But the key thing, unlike the SQL, it's not indexing, it's just partitioning the files into chunks so you can more easily extract data. And the partition by time is very natural because all the data you normally upload there is time-based, like log files, say BGP updates on Netflow information. This slide kind of outlines the whole process of getting data in Cosmos. So from collectors to SLB and then to Cosmos. So like 4 stages. First, you send data to any cast IP address, then it gets forked to multiple collectors, and then all these guys, or some of these guys, get this data and upload to the Cosmos cluster for analysis. And as you can see, it's a very simple concept. You get text files from the collectors, normal CSV files, just Netflow, syslog, whatever data, and then you just simply upload this in a special process. Let's say every 5 minutes, send all this data to Cosmos. And the nice thing about it, the diagram shows a single front end before Cosmos, but in reality, what you do, this front end redirects you to the actual server on the back end. So all the collectors may import data to Cosmos almost like in real time and avoiding any bottlenecks in between. So there's no load balancer bottlenecks in between. You simply upload data to one of the servers. And then Cosmos backend takes care of data replication. Okay, so now you have data in Cosmos, and you need to process this data. And Cosmos uses language known as scope, which is very similar to SQL in its structure, deliberately, such that people can easily transition from SQL to scope. There are 3 differences, right? You can write extensions for scope in C#, of course, since Microsoft language. And there are some operations that don't exist in SQL, such as reduce, for example, which directly maps to MapReduce paradigm. But most of the times, scope queries look very much like SQL. So select, count, join, group, and so on and so forth. But in behind, scope optimizer and compiler transfers this into a computation of the cluster and just uploads the jobs and starts the processing for you. Okay, so before we talk about some of the analysis you can do, this is the data you can get in Cosmos. Let's say some examples of data we have in Cosmos, just the tables. So the flow table, which includes the data from Netflow, sFlow, IPFix, just basically one huge file. We'll append this data from multiple sources. With other information which you need for analysis, let's say topology data, information on your interfaces, the descriptions, indexes, and something you can use to actually add some meaning to Netflow data. There's also a BGP table, which essentially includes all the BGP prefixes from all devices you collect, say, for the past, say, 1-2 hours. So this basically builds the full BGP view for every device in topology. And this is something you can also use for analysis as we show further. And the last one is various grouping factors, let's say GeoIP mappings or mapping of IP addresses to application clusters or environments or things like that. Something which allows you to extract more data, let's say compress the data into more meaningful reports when you need this. Okay, so as usual, there are some issues data analysis. This lists the 3 most common things we encounter. So first one is, of course, data duplication. Let's say you have a flow that crosses multiple devices in the network. So this one is going to be reported to multiple times in your system. And normally there's some tricks, there's some things you need to do to remove that duplication. The nice thing about Cosmos is that it's really easy to avoid duplication by simply running a query which takes all these copies and essentially runs the average function across them. So you do a very simple correlation. If 2 flows are very close to each other in timestamps, and if you block different devices, you simply run average and get you fix this duplication problem very, very quickly. Just one query in scope fixes all this. Secondly, sFlow is essentially flowless. So when you get sFlow sample, there's only one timestamp and one packet. So how would you build the actual flow out of this? Well, once again, it's really easy to do this in scope or in any big data analysis. You get all these samples together, you bin this, say, in time intervals, count the packets, and you get the flow. So essentially, you just create a flow out of the data by simply running a query on this data. Once again, it's all runtime. It's basically part of a processing logic. So you don't have to think about that. Just one query to extract the flow data from sFlow. And the last thing was sampling. Since we do random sampling, we lose some visibility in data. So obviously, you can't see microflows. You can't see quick requests. Let's say if you sample 1 out of 4,000 on a box, you won't see, say, quick queries. The good news is that this is still pretty much enough for capacity analysis, because majority of all traffic flow is basically large, heavy elephant flows. And comparing the data to interface counters, we found that the error rate is about 5-6% on the capacity side. So it's pretty accurate just for capacity forecasting and prediction. And also, this data is still very, very accurate and enough for, say, DDoS detection. Because those attacks are mostly long-living, so normally don't see very short-living attacks. It's enough to have this high sampling rate and still get useful information out of the Netflow data. So 3 basic reports people always want from Netflow, sFlow, something like that. Top talkers, hey, who is the top talking guy on this link or on this device, or say in between to the data centers. So there's one generic report for top talkers, which takes very generic inputs. Let's say, okay, how would you group guys? How would you count the traffic and which traffic rate you want, say percentiles or average traffic. So it's really easy to get one generic query that can give you almost any variation of top talkers anywhere in the network. Peering router, core router, DCR, say top of rack or a spine device, anything. Same query everywhere. Second one is traffic matrix. So you want to know who talks to whom and what traffic rates are. Let's say build this traffic matrix for data centers or traffic matrix for my peers, how I exchange traffic across myself. Very easy to do in scope. Once again, maybe like 1 page of scope script to do all this analysis, and runs pretty quickly if you don't ingest too much data to process. But sometimes, say, if you analyze a month worth of data, the actual analysis may take, like, say, 5-6 hours sometimes. And last on forensic, people want to know who talks to whom, right? Is there anyone who talks to someone he's not supposed to talk to? Let's say if the servers actually try to start connections outside for some reason. So there are some limitations, of course, because of sampling, but still found this to be pretty useful to discover traffic patterns that we don't expect of a network. Second one is a more, say, advanced report, say, DDoS detection. And it's not that hard, actually, to detect DDoS attack in most cases, although you get all the false positives. It's a very simple logic. DDoS is when someone gets hit by multiple senders of traffic, and this flow somehow deviates from normal profile. So you have to build a profile, let's say percentiles of traffic, for all destinations on the network, which is actually easy because you have all the data in one storage. So you can use one query to build the profiles for every possible IP address of your network. Let's say all the servers, all the VIPs you care about. And then you compare for every time interval if there was traffic rate exceeding for this IP address, and if this IP address was hit by multiple senders. And then just normal processing, post-processing, it's about, say, maybe 5-page scope job, which gives you the actual victims and attackers for every time interval you care about. So you run this job once, say every 5 minutes, and you get these possible victims and possible attackers for every time interval. Very simple, apparently, and really easy to extend, so you can add more logic and more processing if you want. Things like routing performance. As I said, we have BGP data in this large storage as well in Cosmos. So it's really easy to take Netflow data and map this on BGP stuff and on topology information to find out how far is particular entry point or egress point of a network from the actual destination IP address in the data center. Of course, there are limitations because, say, BGP table only has ASPEF lengths, right? So you can't get very accurate estimation. But this report can give you like some basic picture of how efficient is the selection of ingress and egress points of your network. And this report requires you to take BGP data and join it on Netflow data. So 2 large data sets, something that is hardly possible to do, say, using SQL databases because of complexity of underlying implementation. And say the last one is HoH Optimization. So using Netflow, you can quickly build a picture of all links, all edge links, find the hot ones and the cold ones, and see if you can move some prefixes around. And of course, you can't move prefixes just like that, say from one link to another. There has to be some constraints, right? The new link has to be close to the other one in the Telemetry, and it has to be close to the actual destination in the, say, ASPEF metric as well. But all this logic could be easily put in scope, and it can give you the list of prefixes that you may move to, say, to shuffle the load from hot links to colder links. Well, not something you can actually use in production right now. It's more of an analysis job, but it's perfectly possible to use this to optimize the edge routing policies. So in other words, this is like a simplified version of Cisco OER or optimized edge routing implementation. So these were some of the examples. The nice thing about the big data analysis is that the number of queries or processing logic is only bound by imagination. So you can do anything, any type of queries, and computation power is sufficient to give you almost any answer, maybe like within 1 to 2 hours for almost any data set, even if it's few months large. As I said, we didn't actually look to build a system that does real-time processing. So it was mostly for offline data analysis. But it was good enough to actually give us reports as fast as every 5 minutes of real time. So let's say the data you get from the system might be as fresh as 5-minute delay, which wasn't too bad. But getting to actual, say, instantials analysis and instantials response is a different problem. Normally involves different systems and not, say, just Hadoop and Cosmos. And of course, the other motivation was the cost. It's much easier to do this using Cosmos and server pools and all this infrastructure you already have, because it's low cost, it's already built, and it's fungible. So as opposed to trying to create new server pool, say run MS SQL or MySQL, mostly MS SQL from Microsoft, it was much easier to go and focus on the reusing the existing big data clusters. Well, now the last question is, what does this mean for audience, right? It's not like many people have these server pools and DC clusters in Cosmos at their hand, but it's perfectly possible to build your own Hadoop cluster. Not too big, maybe like 5-10 servers in one rack, so single switch, small cluster. That's already enough to process Netflow data for almost any ISP, right? If you have, like, say, 8 terabytes hard drives or something like that, it's really easy to have a storage to fit this data for, like, maybe a few months worth of information. And load balancing piece is very tricky as well. It's mostly EZP data that you get, so you can take, say, F5s or netscalers and turn them into the L3 DSR modules, which work perfectly for you, or you can simply use ECMP routing to do the same function, because UDP data does have to be hashed consistently onto the servers. And also, this exercise, let's say putting Netflow on Hadoop, could be used as a first step to big data, because many companies kind of resist moving to big data because they have large investment in, say, SQL storage and SQL data analysis. And SQL is perfect for some problems, but NoSQL, this big data stuff, is really good for things that are, let's say, structureless, append only, and don't require any, let's say, advanced logic to change and update data. Let's say log analysis is a perfect example. And you can always look at Netflow as a large-scale log analysis problem. So I hope this will be helpful for someone who's looking to build the same analysis system in-house. But thank you very much. If you have any questions, I'm all open.
All right, thank you very much.
All right, thanks, guys.